So we're at the end of the class for 1311, work problems for chapter 11. These are not particularly difficult. The ones you'll want to really focus on are the phase diagrams and the Clausius-Clapeyron equations. Let's go ahead and move on to the next slide. So credits here, mostly it's going to be from Brown and LeMay and Zumdahl. A lot of these problems came from Zumdahl's chemistry, a few from Brown and LeMay, and also from Mr. Mack's AP website, which is not listed here, and occasionally from McMurray. Next slide. And the solutions here are provided by myself, all rights reserved. Next slide. So we've already said this. Next slide. All right, so this is just a review of logarithms and logs, base 10 logs. So if you're not really good at this, you may want to pause right here and just look this over. Otherwise, let's go ahead and go to the next slide. And again, you may want to pause this and look this over if you're not familiar with it. So how to do exponentials and logarithms on the calculator. So look this over if you want. Next slide. The Clausius-Clapeyron equation can be done in two different ways, as we talked about in the lecture notes. You can either do it just the basic equation, which is in the form of y equals mx plus b. And so if we look here, now let me get my marker working. We've got y, we've got x, we've got b, and we've got m. So we've got four different things going on here. So if we're given everything but one thing, we can figure out the other thing. If you replace m with delta H of vaporization over r, then you're going to be replacing the m basically with the delta H of vaporization, because we know that r, anyway, the c here is going to be replacing the b, where that c is just a constant you look up in a table. So we can do problems two different ways. We can either do them this way, which I refer to as the stationary way, or we can do them with a before-after scenario. And you don't decide which one to choose, which one you want. You have to go by what's given to you in the problem statement. So if they're giving you in the problem statement that you have a temperature 1 and it has this pressure, and a temperature 2 and it has this pressure, then, or if they're asking you to find the second one, then you would have to use the modified form of the Clausius-Clapeyron equation, where you've got the, the form that has the T1, T2, P1, P2 in it. Otherwise, if they just give you something, which they, and typically my experience is they don't do this on the final, but if they did, and we will have a question like that here, and probably on my test we will, where you just have this form, where you just have this basic form, and for example, they give you, or I give you C, and they give you one of the other, two of the other three things that you need to have, and you have to figure out the fourth thing. So let's go ahead and look at a problem next. So here's an example of that. So notice here they're giving you T, they're giving you the C, you have to look it up, and the delta H of vaporization. So what are we not given here? Well, we're not given the pressure, right? So they're asking us to find that. So what is the vapor pressure? So which equation are we going to use? Just the one that we were just looking at, where you wind up with logarithm of P equals delta H over R times 1 over T plus C. Okay, so we're given everything except P. Now, in this case, that's good, right? I mean, if you're good at algebra, you already saw that, because that means that we've already got what we're looking for on the left-hand side all by itself. So we can just substitute in, plug and chug the things on the right, find the thing on the right, and that's going to give us the logarithm of the vapor pressure. So we're going to have minus delta H of vaporization. We want to convert this from 35.65 kilojoules per mole to 35,650 joules per mole. That's going to be multiplied by 1 over the absolute temperature. And then C would be added to that, and that's plus 18.8, no units. That's because you can't take the logarithm of anything, that any units, or I mean, some problems, there are some problems in chemistry where you do that, but you have to know what units to put back in on the other side. Anyway, let's go to the next slide and look at the answer. So here's our equation, and we know everything except this. So, but that's what we're trying to find. So delta H of vaporization, we want to convert this from 35.65 to 35,650 joules per mole. Divided by R, always 8.314 in this problem, this type of problem. And then 1 divided by 280 is 1 over T. That's this part right here. So 1 divided by 280, and I wrote it out as 0.0357 k's to the minus 1. And then just add on at the end of this plus your C. So we wind up, we're going to divide this by this. I mean, it's just algebra, just math. So when we do this, it turns out that we wind up with the logarithm of the vapor pressure, what's on this side of the equation over here, equals 3.492. So we raise both sides of that equation to e to the power of, and we get the vapor pressure, just without the logarithm, equals e to the 3.492, which is 32.85, and that's all you have to do. All right, so, and then this is one where you have to remember that when you do this, you're going to have to take the logarithm of a pure number here. In this case, it's 3.492. And so you can't take the logarithm of units. So in this particular problem, and for problems like this, you just have to remember that you have to supply the units at the end. So instead of 32.85, the answer would actually be 32.85 torr, because that's the way this is set up. Next slide. Okay, here's the other form where you're going to have a before-after scenario. So usually on these you'll be given the two temperatures and one of the pressures. This is one way you can write this equation, or you can subtract logarithm of P1 from both sides and then do a little logarithmic manipulation where you wind up with the logarithm of P2 over P1. So you can use any of those. So use the one that's easiest for you to be able to do the problem. This is a before-after problem. Let's look at it. So the vapor pressure is given for, this is going to be P1, is 100 millimeters of mercury. You can leave it in millimeters of mercury. And then it's at 34.7 degrees centigrade. We need to convert that to Kelvin though. So I mean, you can never leave those as degrees centigrade because the ratios will be off. So add 273 to that. That's going to be your T1. So here's your T1 and here's your P1 over here. And then here's your T2, 65 degrees centigrade. So that would be added to 273. And then we're supposed to find P2. So you could actually leave it in this form, the way it's written here, and just put in everything else. And that would be the easiest way to do it. Or you can rearrange as we've done in the past. We also need the delta H of vaporization, and that's given here. And that's 38,600 joules per mole. Next slide. So what I've done here is I've just left everything the way it is. So we were given P1 as 100 millimeters of mercury in the problem statement. So take the logarithm of 100 and you get 4.605. And then T1 is going to be whatever you get when you add 34.7 to 273, which is going to be 307.9. And then T2 is, oops, let's see, is that right? Yeah. And then T2 is going to be whatever you get when you add 65 to 273, which is this number right here. And then everything else is already basically given. The 38,600 joules per mole is just the delta H of vaporization, and this is R. And so all we have to do is do these two little calculations. I recommend you write them down. And then, I mean, because if you try to do all of this continuously in the calculator, it gets really confusing. I mean, you could use your memory if you want to. If you're really good at it, you can do that. Just be careful. So 1 over 307.9 minus 1 over 338. And then whatever you get for that, you multiply it by this ratio, which is whatever you get when you divide 38,600 by 8.314. Okay, and then add that to 4.605. And when you do all of that, and you should do this, you should get 5.956. Okay, so I recommend that you do that just for your own sake, just to make sure you can. And then raise both sides of this equation right here to e to the power of, and you get that P2, where the logarithm is going to vanish, P2 equals e to the 5.956, which is 386.1 torr, or millimeters of mercury. It's the same thing here. So again, you just have to remember to put that in. So there you have it. These are really the hardest problems in this chapter. And really, I mean, in some senses, only really difficult thing in this whole chapter, other than maybe the phase diagrams. So, and they're not hard. So you just basically see here that you just have a plug and chug situation here. It can be a little bit harder if you have question where they ask you to find T1 or T2, because then you have to do a lot of manipulation and rearrangement of that equation to get what you want on one side by itself. Or you don't even have to really do that. You can just do it the way we just did this one, and then at some point get it to the point where you can rearrange it more easily. But anyway, but basically these problems are not that difficult. Anyway, so let's move on to the next one. And this is the other thing you're most likely to see on the final exam. So this is the phase diagram type problem, and I warned you about this in the lecture notes, right? I told you that they just give you the diagram with nothing written on it. So what is going to go, let me just see if you can remember, what's going to go right here in the middle? What phase is that going to be, and what phase does it have to be? It has to be the liquid phase, because you've got to be able to go from the thing in the middle to either solid or gas. So this, the way that they always set them up, this is going to be the gas, this is going to be the liquid, and this is going to be your solid over here. And notice that the way this line goes between solid and liquid is the way most things go. So this is not water. I mean, and actually you could ask that, like maybe I will on my exam. I may just ask you, like I might give you this diagram and ask you if this is water. And the answer would be no, it can't be, because water goes like that, not like the way it is here. So this is going to be something like carbon dioxide or something. It's something that you can't change it from a solid to a liquid by just increasing the pressure. But that's another way you can ask this. All right. So you could ask another question from this. You could say, could you convert this from solid to liquid by just increasing the pressure? And the answer would be no. If we have one later with water on it, I'll show you the difference. Okay, so this point right here, E, is going to be what? It's going to be your triple point, and G is going to be your critical point. And if you came straight down, you'd have your critical temperature. And if you go straight across, you'd have your critical pressure. Let's see, this line between E and D here is between the solid phase here and the liquid phase, or sorry, the gas phase here. The line here between E and B, this line is between the solid and the liquid, and this line is between the liquid and the gas. And up here, H would be the supercritical fluid. And then they're also asking at the end, which phase is denser, solid, or liquid? And the answer is the liquid phase. Sorry, the solid phase for this one. So here, the solid phase is going to be denser. In water, the liquid phase is going to be denser. And before we go to the next slide, let me just explain what I just said. So for water, remember the line goes like this, and the reason the liquid is more dense than the solid is because when you freeze water, you're freezing it in the shape that it's in when you've got hydrogen bonds that are holding the water molecules in apart in little pockets. So you have air pockets in there, so the ice is actually less dense. And the easiest way to remember that is just to remember that ice will float on water. So if you have a glass of water and you want to cool it off, you put some ice in it, the ice floats. That means the ice is less dense. Okay, let's go to the next slide. Okay, so these are all the answers that we just talked about. So if you want to pause here and look at these some more, you can. Let's go to the next slide. All right, here's another one. What is B going to be here for this phase diagram? What is B going to be? So I keep harping on that. This is going to be the liquid, right? What is A going to be? Well, A is going to be the solid or the gas. It's going to be the gas, and that's just by convention. And then this one over here is going to be the solid. So we go solid, liquid, gas. What's this point right here going to be? It's going to be the triple point. This area is the area that's between solid and gas, and then of course this is between solid and liquid. This is between liquid and gas. This is the critical point up here. The critical temperature would be about right here. Well, it's actually marked right here down on the x-axis, and this is the critical pressure. Supercritical fluid is going to be the area up here. And what else can we say about this? Oh yeah. Okay, so it isn't asked, but is this water? Let's just ask it straight out. Is this water? So look at the line right here between solid and liquid. If it's going to the right, it's not water. Water has to go like this. So the other question I could ask is, if I increase the pressure, can I melt this? And the answer is no, because if you increase the pressure, you're just going to be increasing the pressure. It's not going to do anything. So if you start off with a liquid and increase the pressure, then it will go from a liquid to solid. But if you start off at a solid, you can't melt it by increasing the pressure. So if it were water, you could do that. So two questions. Number one, is this water? No. Number two, if you start off with a solid and increase the pressure, can you melt it? No. And so if you want to check that for yourself, just try to find a point on here where you can start off in the solid phase and increase the pressure and turn it into a liquid, and it won't happen. Next slide. These are the answers, so you can pause this if you want. Next slide. All right, here's one of our high school problems. Given 400 grams of hot tea at 80 degrees centigrade, what mass do we have to get the whole solution eventually at equilibrium at 10 degrees? So the hot tea is going from 80 to 10, and then the cold stuff is starting off at ice, which is at 0 degrees. It's water. So we have to melt the ice, and then we have to raise its temperature to 10 degrees. So what we're going to wind up is that the hot stuff, however much heat it takes to cool it down to 10 degrees from 80, should equal the amount of heat that it takes to melt the ice. So I'm just going to write that as M, because it's so hard to write with this thing. And then to raise the temperature from 0 to 10. So I don't know how I'm going to write that. So let's just plus raise the temperature, I guess. So I'll write R. All right, so the heat that is given off by the hot tea has to equal the amount of heat that's absorbed by the ice. Okay, the ice, though, has to do two things. It has to, first of all, be melted. Sorry about that. I just accidentally knocked something over. The heat has to be, first of all, put into the ice to melt the ice, and then the ice water at that point at 0 degrees has to be raised 10 degrees. So they have to be equal. The amount of heat that's given off by the hot tea has to equal the amount of heat that goes into the ice, first of all to melt it, and then to raise its temperature to 10 degrees. So you have two things going on over here on the right hand side. Those two things added together have to equal the thing that's on the left. Okay, so what amount of heat would we need, or rather would be given off, as the hot tea cools from 80 to 10? Well, it's going to go 80 to 10, that's a change in temperature of 70, right? 80 minus 10 is 70, so we multiply 70 times the mass, which is 400 grams, and then we would multiply that by the specific heat of water, which is 4.18. So that's going to be the H on the left-hand side. So it's going to be actually minus 70 times 400 grams times 4.18. Right, then for this problem, the fusion here, what we're going to have to do over here on the right-hand side is melt the ice and then heat the ice water up from 0 to 10. So to melt the ice, first of all, notice the units are different here for what they gave us for delta H of fusion. So they give it to us in kilojoules per mole, not kilojoules per gram. So you have to notice that or you'll miss the problem. This is not grams. But so what we just have to do is make a quick conversion. So, and also it's kilojoules, not joules. So we have to multiply this by 1,000. So it becomes 6,010 joules per mole, but we don't want it in joules per mole. We want it in joules per gram. So to do that, we just divide by 18 because the molar mass of water is 18. So 6,010 divided by 18, which I think is 333 joules per gram, is how much we would have to melt it. So we would have to have 333 joules per gram to melt the ice times the number of grams we have, which is 400. And then this term over here is going to be 10 degrees because we're going from 0 to 10 times the 4.18 and then times the mass, which is 400 again. And so what we're trying to do is figure out the mass. Over here, the mass of ice, I said 400, but actually that's what we're trying to figure out, right? So it wouldn't be 400 for these two terms on the right, it would be X. So let's go to the next slide. So on the left-hand side, we have 4.18, which is the specific heat of water, times the 400 grams times minus 70 degrees centigrade, which is minus 117,040 joules. Now, what we do to the ice has to be the same amount of joules. Okay, it's just that it's going to be plus instead of minus, but it also has to be plus 117,040. And that's going to be a combination of what the amount of heat would take to melt the ice, whatever mass is of the ice, and then also to raise the mass of that water from 0 to 10. So I wrote the mass of the ice as x here and also here. On the left-hand side, that's going to be to melt the ice. So here it's to melt the ice, and here it's to raise the ice water's temperature from 0 to 10. So we've talked about this before. And when we add these two terms together here, we have to come up with 117,040 to match the amount of heat that was given off by the hot water. So can you see this? So this is not really particularly difficult. So all we have to do is take this one equation that has one variable and solve for x. This one right here. So once we do that, once we get x, that's going to give us the mass of the ice. So just to simplify it, 333.9x plus 41.8x, here where I've multiplied the 4.18 times 10, equals 117,040, where the 117,040 is what we get when we take the delta T from 80 to 10 for the hot T. So that's going to be minus 70 times 400 times 4.18. So we already talked about that before, so we need the same number down here. So that's where this number right here came from. And then just combine your terms here on the left-hand side, and you get x times 333.9 plus 41.8, which is 375.7. X equals 117,040. Just solve for x, and your x is 311. If I were you, if you have time, if you're doing a test, I would go back and substitute in 311 up here for x and see if you get the right answer. But you should. Okay, next slide. The next ones are going to be from Mr. Mack's website. Next slide. So number 6, based on molar mass and dipole moment, which should have the highest boiling point. So if you look here, all of these molecular masses are about the same. What's actually going to determine the boiling point here is going to be the dipole moment, and the higher, as we said in the lecture notes, the higher the dipole moment is, the higher we would expect the boiling point to be. So which one of these has the highest? Well, obviously this last one, this CH3CN, acetonitrile. So we're going to expect that this one is also going to have the highest boiling point, because the fact that there are very strong dipole moments means that these molecules of acetonitrile are going to be held together really strongly. So let's just go with that. So CH3CN is answer choice B. Next slide. And that is actually the right answer. Next slide. All right, so we've talked about this quite a bit. When the phase diagram for a substance has a solid liquid line that goes to the left, like water, this substance will A, sublime rather than melt, B, melt rather than sublime, C, cannot be liquefied above its triple point. That's a nonsense answer. D, can go from solid to liquid within a small temperature range via applying pressure. In other words, if you increase the pressure, you can force those hydrogen bonds to break and turn it into a liquid. And we've talked about that on numerous occasions, right? So this looks like the right answer. Let's just look over E. Cannot go from solid to liquid by the opposite. So this is just the opposite of D, and this is the case it would be if you had a solid liquid boundary line that leaned to the right, like carbon dioxide. But we don't have that. We have one that leans to the left, so the answer is going to be D. Next slide. Next slide. In general, the vapor pressure of a substance increases as blank increases. And remember, this is one of the general things that we mentioned before. It's just as a general rule, if you increase the temperature, you increase the vapor pressure. And that's independent of anything else that's going on, like polarity or dipole moments or any of that. So our answer here should be E, temperature. Next slide. And it is. Next slide. Of the following substances, which has the highest boiling point? So we look across here, we're looking for things that have polar bonds, and then in particular if they have hydrogen bond possibilities. So First of all, CH4 is not polar, and CO2, even though it has two polar bonds in it, remember we said it's not polar, right? Because the CO on one side, the polarity cancels the CO on the other side, right? Because they're pointing in a straight line opposite of each other. So actually CO2 doesn't have any polarity or dipole moment at all. CH4 doesn't either because it's tetrahedral, and krypton doesn't either. So all of those are zero, so they don't hold each other together, so they won't make the boiling point go up. So the two possibilities that are left are NH3 and H2O, and they both do have polar bonds. The molecules are polar for both of those, and they also have hydrogen bonds. The difference between NH3 and H2O then would be that they both could have higher boiling points than we might expect. But this N right here only has one lone pair, right? Whereas the O here has two. So theoretically, this O here can make two hydrogen bonds, while the N here can only make one. So we expect that the H2O would actually have the higher boiling point than the NH3. Next slide. So A. And the answer is A. Next slide. Okay. Of the following, blank is exothermic. So we're going to need something where you're going from either a vapor to a liquid or a liquid to a solid in order for this to happen. And the reason is because if you're going from a solid to a liquid or a liquid to a gas, you got to put heat in, and that's endothermic. Now, if you look at all of these choices here, everything except A is going in the up direction. In other words, for D, you're melting, you're going from solid to liquid. For C, you're going from solid to gas directly. For B, you're going from liquid to vapor. Only for A here is the process going in the right direction to give us the right answer here. Freezing, you're going from liquid to solid. That means you're going from a higher state of heat content to a lower state. So the heat is given off as heat. The energy is given off as heat. So the answer here is going to be A. Next slide. Next slide. The vapor pressure of any substance at its normal boiling point is 1 atmosphere. Remember, we talked about that before. We said that whenever you're boiling, like water, for example, at room temperature, didn't mean to say that, at sea level, then you're going to have to boil water. You're going to have to heat it up to 100 degrees. And the reason you have to do that is to overcome the atmospheric pressure, which at sea level is going to be 1 atmosphere. So the vapor pressure of any substance at its normal boiling point is going to be 1 atmosphere. You'll need to remember that. Next slide. Next slide. Okay, here we have another phase diagram. Let's see if we can fill these things in. I mean, we can do the answer to the question they ask, but let's just fill in the whole thing here. So first of all, is this water? Is this water? The answer is no, right? Again, water, it would have this line would be going off this way. So the next question that follows with that is, can you change this from a solid to a liquid by applying pressure? And the answer is no. So what is A? So A is going to be the triple point. What's B? The critical point, and then this temperature here would be the critical pressure, right? The line between A and D is what? It's the line between solid and liquid. So remember, liquid always goes in the middle. The line between A and B is going to be the line between liquid and gas. The line between A and C is going to be the line between solid and gas. What did we leave out? Okay, let's go ahead and answer the question. So segment blank corresponds to the conditions of temperature and pressure under which the solid and the gas are in equilibrium. So that's going to be right here, A and C, right? So the answer is going to be A and C, and that's going to be answer choice E. So before we, and then the one thing I left out, I thought there was one thing I should have mentioned in addition to what I did, is that this is going to be the supercritical fluid up here. So this is going to be the supercritical fluid, and I think that covers just about everything on here. Let's go to the next slide. So the answer is E. Next slide. We're almost done. Large intermolecular forces in a substance are manifested by things like high critical temperatures and pressures. Let's go to B. High boiling point, yes, because the forces are holding this liquid together, making it harder to boil. It would also mean that the melting point would be higher. And also, along with that, the heat of fusion and vaporization would be higher because that goes right along with the boiling point and the melting point, right? You have to put more heat into it to melt it or vaporize it because the intermolecular forces are holding it together so tightly. What about low vapor pressure? Well, yeah, that one's actually true too. So we've got all of the above here. The reason you have low vapor pressure is because these large intermolecular forces are going to hold these things down in the liquid or the solution and keep them from evaporating. So the pressure of the things that are evaporating will be less. So that's going to lead to your low vapor pressure here. So the answer should be E, all of the above. Next slide. And that, no, there's one more. Let's go to the next slide. The enthalpy change for converting 1 mole of ice at minus 50 degrees to water at 70 is blank. Okay, so we've got 1 mole of ice, but it's not at 0 degrees. So let me try to draw this. So we've got ice at minus 50, and I'm not going to put that in because it's so hard to write with this. And then what we're going to have to do is we're going to have to raise the temperature of the ice up until we get to 0. And then we're going to have to melt the ice. So it will stay at 0 until all the ice is melted. And then once all the ice is melted, we're still at 0 degrees, but now we have water. And then we need to raise that up to 100 degrees. And then, well, actually, it only wants it to go to 70 degrees, but that's okay. So we want to raise that up to 70 degrees. So here, I'll try to write 70 here next to this so we know kind of where we're at. So this is where we're going to stop. So we have how many steps here? We have to, first of all, raise the temperature of the ice. So this would be step 1, and then melt the ice would be step 2, and then raise the temperature of the water would be step 3. Okay, so the question is asking how much total energy or enthalpy we would have to put into this to do this. So we just have to figure out 1, 2, and 3. So why don't we start with 2, because it's giving us the delta H of fusion in kilojoules per mole in this case. So it says it's 6.01 kilojoules per mole. So change that to 6,010 joules per mole, and that's going to be the amount of energy that is required to melt. So right now we're doing number 2 here. So that is going to be just 6,010 joules per mole times the number of moles, and the number of moles is 1. So it's just going to be 6,010 joules. So our 2 here is going to be 6,010 joules. Okay, for the 1 and the 3, we're told we have 1 mole of ice. For number 1 and number 3, it's easier if we convert that to the number of grams. So how many grams would make up 1 mole for water? And the answer is going to be 18. So 18 grams would go here. So 18 grams. And so for the first part, we haven't ever done this before. The specific heat of ice is what we need here, and it is 2.09 joules per degree per gram. And we have 18, so we're going to have to multiply 18 grams times the 2.09, and then times the number of degrees, which in this case is going to be 50, right? Because we're going to have to raise this from minus 50 to 0 to get it to the point where we can melt it. So number 1 here down at the bottom will be the specific heat of ice, and it's different from water, notice. So it's not 4.18, it's 2.09, which, I mean, if you think about it, that's about half, right? But anyway, so it's 2.09. Actually, it's exactly half, right? I'd never noticed that before. Anyway, 2.09 joules per gram times 18 grams, because we have 1 mole, which is 18 grams. And then times 50 degrees, because that's the temperature we have to raise it. And then number 3, see if you can figure out what that would be. So you might want to pause it and just see if you can figure it out before I tell you. All right, so for 3, we're going to be multiplying 18 grams times the change in temperature, which is 70, times the specific heat of water, which is 4.18. So, I mean, I won't do an estimate of that, but once we figure out what that is, just multiply those, then just add 1 to 2 to 3, and you have your answer. So let's go to the next slide and look at that. So for the first part here, this is for raising the ice, the temperature of the ice from negative 50 to 0. 18 grams, which is 1 mole of water, times the specific heat of ice is 2.09, times 0 to minus 50 is 50. And then add your 60-10 to melt the ice, and that was number 2. And then number 3 was the 18 grams, again, which is 1 mole, times the specific heat of water times 70 Kelvin. So add all 3 of these together, you get 1881 plus 6010 plus 5267, and that adds up to 13,158, which is roughly 13.16 kilojoules, or you could write it as 13,160 joules, and that's the answer. Right then, so that didn't take too long, so that wraps up this course, and I hope that this will be helpful to you. So good luck on the final exam and on your last exam, and if you have any need for any help, please email or call.